Okay, guys, we will get started at 7:05 p.m. Okay, let's give it maybe 5 more minutes for more attendance. All right, so let's get started. Can you guys hear me? Test, test. Can you guys hear me? All right, so let's get started. So thank you for joining us. Today we're going to have our 2022 Euclid Math Competition Bootcamp. Today is our lecture number 1, aka it's an open course. So in today's lecture, we're going to be giving you guys a little bit information how the 2022 Euclid Math Competition works, and then give you guys more idea how we're going to help you guys organize our bootcamp. So before we get started, to like the technical details. So I want to answer actually a bunch of questions. There are some high frequent questions people like student parents keep asking me regarding the math competition itself. So that's pretty much what we can focus at the very, very beginning. Okay. So at the very beginning, we're going to talk something about understanding the Euclid math competition. You're going to understand your enemy. You're going to know your friends as well, right? So the first question is, how does the Euclid math competition works? So generally speaking, the Euclid math competition contains 10 problems, and each problem worth 10 marks. And the total time you're going to have to finish the math exam is 2.5 hours. So for each problem, generally speaking, it should have A and B 2 parts or A, B, C 3 parts. So sometimes, especially for the early problems, let's say question number 1 all the way to question number 5, question A, B, C part might not be really relevant. So let's say question number 1, A part might be a quick calculation, while B part might be a geometry problem. Okay. However, especially from question number 9 to question number 10, as long as the question gives you A, B, C 3 parts, these 3 parts must be relevant. So that being said, as long as you finish the A part, which is considered to be relatively easy, most of the time, the conclusion you got from A part would be very easy to be applied to the B part, and then maybe A and B part altogether will be applied for the C part. So that being said, especially for the last 2 to 3 problems, you can't really segregate A, B, C 3 parts. Whatever you get from A part must be very easily transferable and applied for the B part and C part. All right. And then the type of questions. So basically, Euclid has 2 types of problems. One type is you just basically give an answer, just like our Amy, right? As long as you give an answer, you're good. And the other type is you need to give a whole work. You need to show your work. Well, if you do any analysis, you're going to find out, especially for Euclid, for most of the problem, you need to show your work. So this is kind of like different from AMC, right? For AMC, you only have like 5 options. For AMY, you just have to put a number from 0 to 999. So the problem doesn't really care how you get an answer. As long as you can throw a dice, right? You can toss a dice, you can get your answer, you're good. However, for Euclid, you need to show your work. It is extremely important. All right. So moving forward, second part, why do I need to participate the Euclid exam? Is this something useful? The answer is yes, especially when you want to apply for the Waterloo University. You know, especially when you apply to Waterloo University, very, very hot, like majors, the mathematics, the computer, you know, so on and so forth. Right after your application, the system is going to be automatically sending you an email. The email wording is very polite, saying that, okay, thanks for your application. We strongly recommend you to participate the upcoming Euclid contest. Even the wording is very kind, but trust me, due to our statistics, everyone who successfully got an offer from the very popular major, they definitely went to the Euclid exam, and all of them did a good job. So that being said, even though Waterloo University didn't put the Euclid exam as kind of compulsory, but in the real practice, having a good score in the Euclid exam will be extremely important for Waterloo University applications. All right. And the second part is, if you do the good job for your Euclid exam, especially for grade 12, you will be able to enter an entrance scholarship, worthing from like 1,000 to 10,000. It really depends on where you stand. So if you go to like the Waterloo website, there is actually a section talking about the admissions and the scholarships. And here they put they actually specify the Euclid exam is very important. And especially they put it here. If you want to go to the Faculty of Mathematics, which is the most popular faculty for most of the students, so you must write at least one of the CSMC or the Euclid in order to be considered for new scholarship. So if you do comparison between the two, actually Euclid is way more important. So that being said, Euclid exam is actually very practical. It helps you to get admission to the Waterloo University and also help you to go to the new student entrance scholarship. All right. So the third question, is there any certificate, right? Most of the exams, the AMC exam and most of the Waterloo exam, they have a certificate in order to recognize you're being distinguished, for instance. Yes, the answer is clear. You have a certificate as long as you mark up 25%, the top 25%, you'll be able to receive a certificate. Okay, so it says every student scoring top 25% of all the competitors will receive a certificate of distinction. All right, 25%, you're going to receive a certificate. If you want to do something even better, you want to have a more shining, kind of like supporting document for Waterloo application, you better go from 25% to a little bit higher. You can go to the top 5% to top 2.5%. You're considered to be the honor roll. As long as you're there, your application, especially using the Euclid exam, will be very straight. Okay, very powerful. Okay. Question number 4, are the problems in Euclid exam, they're easy or they're fair or they're difficult, right? I think this is a very common question that every student wants to know. So let's do a quick refresh. For the Euclid exam, it always have 10 problems and 10 marks for each problem, right? So here we actually have a statistics, in the last 10 years, for all those problems from question number 1 all the way to question number 10, if we do an average, all the participants, okay, different grades, different country, let's do an average, a global average. What is the average score each student they can get, especially for all those 10 problems? Okay, so this data actually tell you a lot of very useful information. A quick look at, you're going to find out in the first 4 problems, they are considered to be easy problems. You see, most of the students, they got a full mark, 9.1, 9.5, right? They're considered to be relatively straightforward problems. Okay. From question number 5 to question number 7, you see, the average score will be from 5 all the way to 7, so on and so forth. Bear in mind, this is not for one student from Canada, not from one student from a certain region. It's the global score. All the students will make such a statistics. So as long as you can see 5 out of 10 or 7 out of 10, yeah, consider this is something pretty much in the middle, right? Not so easy, of course, not so difficult. All right. And what about the last 3 problems? From question number 8 all the way to question number 10, you will see the number become a little bit ugly, right? Number 8, roughly student only got 1 to 2 marks. Number 9, 1 mark. And number 10, almost no marks, right? You see almost like the decimal. So that being said, all the problems in the Euclid exam, they're not the same complexity. All right, some of them are easy, some of them are fair, some of them are definitely difficult. So that being said, if we do a quick analogy, we can find out from question number 1 to question number 4, they are considered to be easy problems, easy questions, easy peasy, lemon squeezy. You have to do them, you have to do them right. There's no way around. From question number 5 to question number 7, they are considered to be a critical problem. Because check it out, you see, most of the students, they actually make the difference from question number 5 to question number 7. You see, the average score is 5, 7, so on and so forth. If you can make them correct, you'll be very competitive for the entire Euclid math competition, which is very important. I give a name, the critical questions. And also from question number 8 to question number 10, they are the killers. They are going to be very difficult, especially question number 10 is more difficult than Amy problems. So that being said, you really have to know some technologies, some different skills, some strategies, how to solve this problem. These problems, the solution process won't be something you see in a day-to-day basis. You need some special training. And to be honest, in our lecture, we're going to be more focused for the killer problems. Okay, The easy ones, you can do it by yourself. The critical ones, as long as you have some general trainings for the math competition, or you just read the official solution, you have no problem understand all of them. However, for the last 3 problems, they're critical, they're difficult, and sometimes if you just read the solution, it's very confusing. So in our lecture, we're gonna basically focus on the last 3 problems, give you guys a lot of strategies, different methodologies, and how to solve all those problems in a more efficient way, okay? In a more efficient way. So this is our question number 4, the complexity for all the problems in the Euclid exam. Let's go to our question number 5. So what score I need to have in order to be standing out from the Euclid exam? So basically, again, this is like a 10-year statistics for all the Euclid participators. You can see they have like 2 things you want to have a quick look at it. One is the top 2.5%. That's the distinguished overall. That's a very good student. The other one is top 25%. That's the thing that will give you a certificate, right? So let's have a quick look at it. The green line is basically top 25%. It's actually here, right? From here to here. You can see in order to get a top 25%, it's not so challenging. As long as you can do roughly 55 scores, roughly, you'll be good to go, right? So trust me, you have the easy problems from question number 1 to question number 4, right? You have to do them, you have to do them right. And then you have the critical problems from number 5 to number 7. So as long as you can do half of the critical problem, you'll be able to get roughly 55 scores, right? So that being said, like I keep saying, to get a certificate from the Euclid exam is something fairly straightforward. As long as you don't make any stupid mistakes, you'll be able to get your basically certificate. Well, something I want to have a quick discussion is the top 2.5% to top 5%. So that one you need to have, as actually the orange line, you need to have roughly, you see, if you do average over different years, you need to see roughly 83 scores in order to achieve that goal, okay? So the question is, a good score, a good enough score is like 83, but how can I make an arrangement to make sure I can get that 83 scores, right? That is something very important. So basically, here's our strategy, how to make it happen. First of all, question number 1 to question number 4, because like I said, these are actually these are like the basic problem. You have to do them and you have to do them right. There's like definitely no way around, okay? 40 scores, you have to take it. From question number 5 to question number 7, these are the critical problems. Yeah, you can make some mistakes, but your goal is try to minimize the unnecessary errors. So you see you have like 5, 6, 7, right? You have like 30. If you can get roughly 28, that would be no problem, okay? Then moving forward, question number 8 to question number 9, these are considered to be the relatively easy part of the difficult problem. Difficult problem is from number 8 all the way to number 10, right? And number 8 and number 9, they're relatively easier, and number 10 is by any means the most complicated ones, right? So that being said, as long as you can get a part of question number 8, question number 8, question number 9, and part of the B part of question number 9. Okay, you don't have to do all of them, part of them. So totally you have 20. If you can get roughly 13 out of 20, I think this is quite reasonable based on our analysis, based on our trainings. Okay, and then the last problem, question number 10. So most of the students, they just give up question number 10. They have no time, and they don't even have any courage to see question number 10. Even though question number 10 is very challenging, but trust me, question number 10 always have A, B, C, 3 parts. And the A part is always relatively easy compared with the other parts. So that being said, if you can try to work out question number 10, A part, then you can still get roughly 2 scores out of 10, okay? So if you do a quick calculation, 40 plus 28 plus 13 plus 2, that's gonna give you 83 scores. You know what, 83, is already very amazing. That's going to help you to get your distinguished role, so on and so forth. Everything is perfect. So that being said, the most important thing is when you go to the Euclid exam, you kind of have to do some arrangement, some kind of like strategy. You can't take all the exams exactly the same. On the contrary, you need to have some focus. Of course, these guys are very important because they're considered to be critical. And for the following three parts, you also need to get kind of like, you have to give up something, but you have to take something, kind of like a balance. All right, so this is where we come from in order to help every one of you guys in order to have a good score in the Euclid math competition. All right, so number 5. Many of my students, they're asking me, Euclid, is Euclid similar to AMC 10 and AMC 12? Because I have a lot of students say, okay, I only want to go to the States, so I want to do the AMC. Or vice versa, I only want to stay in Canada, I don't want to even think about AMC. So is it like correct or no? So the question is Euclid similar to AMC 10 and 12? You know what? The answer is hell yes. They just copy from each other. And of course, most of the time, Euclid copy from the AMC exams. I want to give you like 2 examples. I think the examples will speak for themselves. The first one is, if you see an exam from 2014, AMC 10, AMC 12B, question number 21. And 4 years later, if you go to 2018, Euclid, question number 8, B part. These 2 questions, they're exactly the same. Only difference is that AMC use 1 graph and Euclid break it into 2 graphs. But in terms of the solution strategies, they're exactly the same. This is a very good example that Euclid directly copy from AMC. Okay. The second example is one of the problem from 2006 AMC 10A, question number 16, and 2015 Euclid question number 8, B part. This part, I don't even have to explain too much. They're actually, they don't even bother change the graph, right? Even the graph, they're exactly the same. So I think 2 examples is good enough. Just want to show you guys, even though you are more AMC player or like a Euclid player, it doesn't hurt. You can actually join both of the exams. All the technologies, all the strategies you learn from one exam will be 100% transferable into another exam. All right, so these are kind of like some explanations. So based on our strategy, how are we going to take care of our Euclid exam? How we want to do our preparations, which is critical, right? So our lecture actually contains 10 different lectures. Today is lecture number 1. And these 10 lectures, we're going to cover the 4 very important topics for the math competition. For the first 3, we're going to talk about the geometry session. From number 4 to number 7, we're going to talk about the algebra session. From number 8, we're going to talk about the combinatorics, the counting and probability section. And the last section, last lecture, will cover the number theory section. Actually, we did a lot of like analysis, use the big data. We're going to go we actually went every single exam in the Euclid history. We actually find out there are some statistics, each kind of like section, each kind of concepts, what is the percentage for the entire Euclid math competition? I'll give a quick statistics, quick numbers for you. You see, for the first one, triangles, quadrilaterals, that was actually 24% in the last 20 years. Lecture number 2, we're going to talk about the circles, like the 3D geometries, that is 8%. Okay, here I want to give you a highlight. 3D geometry, even though it is extremely important for AMC 10 and AMC 12, but in Euclid, it's not that much important. In the last 20 years, it only tested once for the year 2017. There's only one problem from 2017 that tested the 3D geometry. Well, the rest of other 19 years, they never tested. So you can do the math, you can figure out which one is more important. For the lecture number 3, we're going to talk about the coordinate geometry. That's roughly 15%. Okay, and then we actually go to the algebra section. The algebra section, the exponents and the logarithm, that's actually 10%. Trust me, you're going to have one problem every year. No exception, never more than one, never less than one, always one problem. One problem tests you the exponent, one problem tests you the logarithm, okay? Every single year. For lecture number 5, we're going to talk about the functions, advanced function, polynomials. That one is roughly 15%. Lecture number 6, we're going to talk about the trigonometry. Trigonometry is actually roughly 8%, not that much important. Trigonometry is extremely important for AMY, but for AM and also for AMC 12 as well. But for Euclid, for AMC 10, it's not that much important. But of course, every year you're going to see one problem testing the trigonometry. And lecture number 7, we're going to talk about the last part for the algebra, which is the sequence and series. That one is roughly 10%. Also, every single year, there will be one problem testing you the arithmetic and geometric. Okay. Number 8 is the counting and probabilities. That's actually 12%. Every year, you will see 1 or 2 problems. Number theories, that's 8%. Okay. So that's basically our first 9 lectures. We're going to cover everything, the most important thing for the Euclid. And then as long as we go to our last lecture, we're going to do question number 10 bootcamp. Because these days, you know, the complexity is getting bigger and bigger, right? It's not only for Euclid, all those are math competitions. So that being said, we're going to give you guys some special strategies, how you're going to deal with question number 10. Question number 10s are difficult and you need some special help, some special tricks in order to do a good job. So that being said, for this year, we're gonna have a special lecture only talking about question number 10. We're gonna talk about some latest and greatest question number 10s, try to make sure we're all on the same page, how to deal with this question number 10 in a more smart way. Not necessarily a hardcore way, but a smart way. All right. So actually, when I'm talking about this, some student might say, hey, Alex, if you just do a quick calculation, all those numbers, adding them together, is actually greater than 100. Is that right? So why we're having this? The reason is sometimes one question, they can test you multiple concepts, right? Not only a question only for the equation, maybe the equation also have something like the, you know, kind of like polynomial or trigonometry, so on and so forth. So that being said, if you put everything together, you will be able to see such a quick statistics. And also a very quick observation you can find out, if you just check the geometry part, okay? Just the geometry, you can find out if you add 3 numbers together, this is gonna be more than 40%. Okay, we have 4 different sections, right? And the geometry section is actually more than 40%. Does it make sense? Yes, it is. Euclid put a lot of emphasis for the geometry. Okay, you see from the name itself, Euclid, right? Euclid is the name of the geometries. So therefore, having a good understanding for the geometry problems and common strategies for the geometry problem, it would be extremely helpful for us to have a good score in order, you know, to have a good score in the Euclid math competition. Okay, so basically that's how our lecture works. In these 10 lectures, we're basically going to do something like this. Each lecture, okay, this is a boot camp. So we're going to focus on the problems. However, I don't want to just give you the problems because there are millions of problems, right? You can never cover them all. In order to have a good score for the math competition, not necessarily only Euclid, right? Only having the problems not good enough. I think I like to break our lecture into 2 parts. The first part is the concepts. I'm going to help you guys do a quick summary, the most important concepts that you will have to learn in order to go to the math competition. So the concept is more like fish and fishing, right? And then right after our concepts, I'm going to teach you guys some problems. However, it's more like some categories. So that being said, there are so many problems, I need to classify them into certain categories. And certain categories that must have the similar problems in between, right? However, I'm going to say that in Euclid, there are, let's say, 3 major categories. We're talking about the geometry, for instance, and having a good understanding for each of the representative of each category will be extremely helpful, right? We don't do the same problems again and again. but we just want to give you one or two examples, try to cover the most important categories. So this is actually something even more important. All right, so this is actually how our lecture works. Concepts plus the problems, and problems must be classified into the typical classical categories. That's going to be very helpful for you guys to get a hang of it, right? How the Euclid works. All right, I think that's pretty much what I want to say as a quick start. So hopefully give you guys a good idea how the Euclid works and how our lecture works. Okay, if everything is good, let's fly to our lecture number 1, triangle, quadrilateral, and the polygons. All right, if all good, let's jump to our lecture number 1. Lecture number 1, this is a geometry, but we're gonna focus on the triangle, quadrilateral, and some polygons. We're not gonna talk about the circles because we're gonna leave it for our next lecture, lecture number 2. So let's get started. What are the basic concepts that you have to know for the triangle, quadrilateral, all those kind of basic things in order to go to the Euclid exam? So our first part is the concepts. The first one that's so easy, the trigonometry inequalities, right? As long as you have some triangle, what kind of triangle? You should have this basic relationship. The sum between two sides will be greater than the third size. Actually, if you can recall in your textbook, the question, like the problem says, actually you have two sets of equations. One is adding them together. Adding 2 is greater than the third. Or you can do a subtraction, right? If you do subtraction between 2, it must be lesser than the third. But actually, they are identical. Because if you choose this guy, do a quick modification, that's going to be A is lesser than B plus C, right? So that being said, that's exactly this part. So therefore, even though you have two sets of inequalities, but they're not independent, all the subtraction related inequalities, you don't have to remember. You just have to do the add related inequalities, and they are good to go. Okay? Actually, this is one very important inequality you have to know for a triangle. Also, there's another very important inequality that also every single triangle has, is something like this. Sine theta. If I take an absolute value, will be greater than 0, less or equal to 1. Cosine theta, greater or equal to 1, greater or equal to 0, lesser than 1, right? As long as theta is actually an angle from a triangle from 0 to 180 degrees. Is that it? That's a basic stuff. Even though there's something like so easy, but trust me, this is very helpful, because as long as the problem asks you to create or to construct an inequality in a triangle without giving you any special conditions, you need to remember there are two intrinsic conditions for a triangle, right? Even though you have nothing, you will be able to try to utilize these two relationships, help you to do the calculation and generate the entire inequality. Okay, that's our part number 1. Number 2, Pythagorean Theorem. This is what you know from the elementary school, right? If you have like a right triangle, you have two sizes, you're gonna have the hypotenuse will be under root a squared plus b squared. This is like so easy, nothing to say. Well, the only one thing I wanna have a quick emphasize is that sometimes the question will not directly tell you, okay, I have a right triangle, I have like two sizes, help you to determine third one, so on and so forth. Well, on the contrary, the question will directly give you three sizes of a triangle, and you have to be smart enough or vigilant enough to figure out, yeah, this is actually a right triangle. So AKA, you need to know the Pythagorean triples. Pythagorean triple means the three sizes, they can automatically generate a right triangle, right? So there are many Pythagorean triples, and some of them are actually very important. We actually did some quick analysis. So these guys are actually very important. Euclid and AMC tested in their entire history. So if you cannot remember all of them, at least remember these 4. Okay, these 4 are the high frequency problem tested in the Euclid and American exam in the last 20 years. Okay, that's the Pythagorean triple. Moving forward, we're going to go to the most important part for the entire AMC and our Euclid. They're pretty much sharing the same concepts. So AKA the congruency and similarity, right? So we always get started with the congruency. Congruency means the two triangles are exactly the same. There's no difference. They have exactly the same size, they have exactly the same angle, okay? So we're gonna have how to determine two triangles. They are congruent to each other. So you're gonna have the three sizes, side, angle, side, the two sizes, and also the included angle, right? And also you have the ASA, two angles and their included side. And the AAS, you have the angle, two angles, and one of the opposite side of the angle, right? I think this is something you should be so familiar with. And then, especially for a right triangle, you can have only one right leg. The other one is the hypotenuse. Why? Because using the Pythagorean theorem, as long as you have the hypotenuse are the same, one of the right legs are the same, using the Pythagorean, the third one will also be the same, right? So AKA, this is the SSS. Or alternatively, you can say the right triangle always have a 90 degrees here, right? So no matter what kind of size you have 90 degrees are the same. So this is also considered, you can have like the angle as well. So that being said, for the right triangle, there's no need to have too much information. As long as you have one right leg, and one hypotenuse, you're good to go. Well, here is something that I need to basically make an emphasize. I think everyone knows already why we have the SAS, ASA, AAS, but we never have the SSA. Can we have like two sides and also one side's opposite angles are the same? So this is the explanation. Let's say when you have these side and these side are the same, no problem. You have this angle 30 degrees, no problem. And you have another side 6 here. Actually, you can create two triangles. They both have the third side equals to 6, right? This is more like you can use in your compass, making two hits from here. So that being said, you can actually have two triangles. They are according to the SSA determination rule. Of course, only one of them is congruent to the original one on the left. The other one is actually obtuse triangle. For sure, they're not the same. So that being said means what? It means the SSA is not a guaranteed rule for you guys to determine two triangles that are congruent to each other. Never ever use the SSA. All right. Okay, let's continue. So congruency is actually a very strong condition. You want to make sure two triangles are exactly the same. But most of the time, you can't really asking for too much, right? Two triangles, they won't be exactly the same. So that being said, we want to step back a little bit. Instead of asking for too much, maybe I can just ask for two triangles. They're proportional, they're alike. Actually, we use the word they're similar, right? Two similar triangles, they have the same angles and their corresponding sides will be proportional to each other. So that being said, congruency is only an exceptional case of the similarity, aka the proportional is actually exactly the same. The ratio equals to 1, right? But most of the time, similarity is actually more casual, more flexible determination condition rather than the congruency. So what do you have in order to determine two triangles that are similar to each other? Number one, this AA. As long as you have two angles are the same, because the total sum is 180 degrees, the third one will automatically be the same. So also you can have the SAS, two sizes plus an angle. You can have the SSS, three sizes proportional to each other. You're good to go. So here, if we have a very quick comparison between the congruency and the similarity, you can find out in order to determine two triangles that are congruent to each other, at least, you need to have a side condition, right? You can have like 3 sides. One side, I don't really care, but at least you need to have a side condition. However, to prove 2 triangles are similar to each other, side is not so important. As long as you have angle, you're good, right? Or you have side, 3 sides, it is okay, no problem. But there's not as, as strict as the congruency. Congruency, you must have the side. But the similarity, you can have side, you can have angle, it's up to you. As long as you can make sure the angles are the same and the sizes are proportional to each other, you are good to go. All right. So these are actually considered to be the very important part for the 2 triangles, like triangle, very important properties, congruency and similarity. Okay, let's continue. The sine law and cosine law. This is very important in AMC and Euclid as well. You need to know how the sine law works, right? Any kind of triangle, you're going to have a sine law. So what is this R, right? The R is actually the radius of the circumcircle, right? The radius of the circumcircle. This is R. Also, this is actually our sine law. And the second part is our cosine law, right? Cosine law is also very important because cosine law actually gives you a very important property. Check it out. I'll take this as an example. Let's say cosine C equals to what? A squared plus B squared minus C squared 2AB, right? Cosine law is the only one law that make the relationship between the angle and the side. Let's say on the left-hand side, you only see the angle, right? It's only an angle. On the right-hand side, you only see a side. So that being said, as long as the problem gives you a bunch of side with 0 angle information, but at the end of the day, the question asks you to determine some angle information. The most important strategy you're going to use is going to be the cosine law. Cosine law give you this kind of a feasibility that you can determine the angle solely using side. All right, check it out. The sine law does not have this. You see, if you check any 2 equal signs, for instance, the left-hand side, it has a side, it has an angle. The right-hand side also has a side and angle. You won't be able to solely determine the angle solely using the side. You kind of need to have the 2. However, cosine law is like so nice. You can directly determine the angle without touching any angles. Only side is going to help you to determine the angle. So trust me, this is very important for Euclid. All right, continue. We're going to talk about the area of a triangle. How to determine the area of triangle. Trust me, this is crucial. This is very important, not only for Euclid, but also for AMC. AMC and our Waterloo exam, they both put a lot of emphasis how to determine the angle, how to determine the area of a shape. Of course, not necessarily triangle, right? But try to determine the area is crucial for all our North American competitions. So here we're going to do a quick summary how to determine an area of a triangle. So first of all, you're going to try to use the definition. Of course, that part you can learn from the elementary school, right? To use the bottom times the height divided by 2. Second part is the Heron's formula. As long as the question gives you 3 sizes of a triangle, you will be able to basically use the Heron's formula. You can construct the S. S is the half of A plus B plus C, half the parameter, and then under root S times S minus A minus B minus C. That's actually what you need. That's the Heron's formula. And you know what? Actually, a lot of students just remember all the way to here. That's it. But if you can do one step forward, you want to put in the value for S. Okay? Just put in the value for S. Put it here, here, here. Try to do some quick calculations. You can find out this is another way how to determine an area. So that being said means if you already have like this ABC, have like all the things, you can directly remember such a formula that's going to help you to determine our area. Okay? So moving forward, I'm going to ask you a quick question. If the question basically how to determine the area of a triangle when the 3 sizes are provided, Yeah, of course, students. Hey, Alex, you just mentioned the Heron's formula. Yeah, for sure. Heron's formula is actually a very good way. But sometimes there's another way how you to do the calculation. So why I have to know another way? I'll give an example. Let's say you have a triangle. You have like the three sizes, something easy. Let's say, I don't know, 2, maybe 4, maybe 5, for instance. Okay. If I want to ask you to determine the angle's area, the triangle's area using Heron's formula, so easy, right? You just determine S, 2, 4, 5 divided by 2, right? And then you do this calculation. That's it. However, what if I give you some weird numbers? Root 3, root 7, I don't know, maybe root 5, for instance. Okay, if you have such a situation, you want to determine the area again using the Heron's formula, S will be what? Root 3 plus root 7 plus root 5 divided by 2. And then your calculation will be horrible. Your area is going to be S times S minus A, S minus B, S minus C, right? There will be a tons of under root here and here, here and here. That's going to be extremely difficult for you to do the calculation. Is it right? So as long as you see some weird numbers for the three sizes, do you have something easier rather than doing a hardcore Heron's formula related calculation? So the answer is yes. You can use a very famous double Pythagorean theorem method. What is that? Double Pythagorean theorem method means, let's say you have A, you have B, you have C, right? You can basically make a height here, okay? As long as you make a height. So let's say you call this part X. So this part is going to be C minus X, right? Because the two parts add them together is going to be equal to C. So what you can do is you can do A squared minus X squared, which is actually your H squared, right? Using the Pythagorean. That one is also B squared minus C minus X squared. Is that right? Makes sense. You're kind of using your Pythagorean theorem on the left and also on the right. Very understandable, right? All right, so check it out. This guy is going to be very easy to calculate because you have a minus X squared on the left. And you should have a minus X squared on the right as well. So that being said, this 2X squared will be canceled. You can have a linear equation for X, right? As long as you determine the value for X, you just use another Pythagorean theorem. H will be A squared minus X squared. Then you will be able to determine your H. So your area will be 1/2 H times C. So even though you break your calculation into 3 steps, however, there's no more complicated like under root things and multiple them together. Is that right? So even though it looks like difficult, you go for 3 steps, but the calculation will be much more straightforward than using the Heron's formula directly. So that being said, I strongly recommend you guys to remember the double Pythagorean theorem, because from time to time, whenever you see some weird numbers, using the double Pythagorean theorem will be much more straightforward compared with using the Heron's formula. So far, so good. Just want to give you guys a quick heads up. And then shoelace, right? Shoelace theorem means that as long as you have a triangle, you have the coordinates of the 3 different vertices. How can you determine the area of the triangle, right? So that part we have already talked about so many times in our regular lectures. Try to remember this, okay? Do not use the complicated things. Some students determine how to determine the side of this, determine the 2 distance, like the distance between 2 sides, and then another one, and then another one, and then do a Heron's formula or double, like the double Pythagorean theorem later. That's going to take you forever. Try to remember the shoelace, okay? Extremely important. If you check some of the official solution from the Euclid, their solution is very lengthy because they don't know how to use the shoelace. If you use the shoelace, much more faster, okay? So actually, the shoelace theorem can be expanded into more generic form. right? Not necessarily only like 3 different points to go a triangle, right? This is a triangle. You can actually expand it into any kind of convex polygon. What is a convex polygon? Convex polygon means, give an example, if I take any kind of their line, their kind of size, I make an extension, 2 sizes, the entire shape must be on the same side of my extension. So something just like this is considered to be a convex. However, if you have a shape like this is not a convex, right? Because if I extend this line, you're going to see not the entire shape is on the same side. Some of them is on the left, some of them is on the right, right? So this, what we call this convex, right? The convex. So this one is not so important in our high school territory. Our high school territory focuses on the convex. Okay, so you can remember this as a more generic solution, how to determine the area of a convex polygon, provided all the vertex coordinate has been given. All right, I think that's pretty much what I want to say for the most important concepts for our Euclid math competition. Okay, there are still some theorems are not so important for Euclid because you never see that in the last 20 years. However, they're extremely important for the AMC. I just want to give you guys a very quick heads up. Number one is like Stewart, right? As long as you have a triangle, what kind of triangle, it doesn't matter. And you give the measurement for all of this, okay? You have 5 segments, right? You find any point, any kind of point on the BC side, right? And then do a quick calculation. And then you'll be able to find out all those 5 segments, there's a relationship, right? This is actually our Stewart. Okay, so all our kind of like, for instance, angle bisector length theorem or our median length theorem, all of them can be derived from our Stewart theorem. This is very important, especially for Amy, but for Euclid, I don't think we never tested. Something not so important. Second is the many laws. Many laws is also very important for Amy, but of course, like the AMC never tested. Amy laws means there's a transversal line cut a triangle, then you automatically have BP over CP is actually times CQ over QA times AR over RB. So this is going to be equals to 1. Basically, if the transversal line cut the triangle into 2 points and make the extension between, make the intersection with the extension of the third line, you will be able to have such a relationship. This is the many laws. And also the Siva. Siva theorem is also very important. You have any kind of triangle, you find a dynamic point in the middle, make 3 extensions, you'll be able to have BD over DC times CE over EA times AF over FB, the entire thing. You make a circle for the 3 sizes of the triangle, adding multiple them together, the solution is actually equal to 1. Okay? So basically, these are the most important things I want to say for the Euclid. Especially for Euclid, you can focus on the first 6. The first 6 is way more important than the last 3. All right, so far so good. I think this is our boot camp. We already give all the details in our regular lectures. So today we're just going to just do something fairly quick. All right, if all good, it's time for us to have some discussion. Okay, these are all the Euclid concepts. And what kind of problems, what are the typical problems you will probably see for the triangle and quadrilateral part? So generally speaking, there are 3 very important problems. So we'll say typical problems. So what are the typical problems? So there are 3 major categories. The first category is actually determine the area. Like I said, area is like extremely important for all the Euclid and AMC, right? And then Euclid put a lot of emphasis on the areas method related calculation. How to determine the area. And there's actually one thing you're going to see that in Euclid from time to time is a conversion and compensation method. No worries, we're going to talk about it in our next lecture. We're going to give you some real problems in the upcoming lecture. Second part is using the trigonometry / cosine law. This is going to help you a lot in determining some complicated problems. Today, I'm going to give you some example that you will understand why using the trigonometry can be extremely helpful, help you to deal with some relatively difficult geometry problem, and also the cosine law. And the third part is you always want to use the areas ratio equals to similarities ratios perfect square, right? So as long as two triangles, they're similar to each other, the areas ratio is going to be the similarity ratios perfect square. So trust me, based on our analysis, all the problems in the 2D geometry, the triangle, quadrilateral part, these are the three major category of problems that Euclid loves to test you. Okay, today I'm going to give you some sample problems for all of these three categories and give you guys a big idea what you're going to do whenever you see all these problems. All right, so far so good. Okay, before we jump to category number one, there's another very important thing I want to highlight is the writing. Many students ask me all the time, hey, Alex, how can I write? Is my writing like detailed enough or too, like too brave, so on and so forth? If you check the Euclid official solution, always they give you a huge detailed solution, right? Not to say you figure out the solution. If you just copy those solutions within 2.5 hours, you just can't. There are a lot of unnecessary details in the basically official solution. There's too much overhead. So in my lecture, I'm going to show you how to write it in a very straightforward way. Instead of wasting a lot of time to the presentation, to this kind of writing thing, you can expedite. So these are actually something very important in our lecture. Show you guys a shortcut solution for the writing. Okay, if all good, let's fly to the real problems to see these three categories. Okay, let's go to our category number one. Area method, right? Using what? Conversion and compensation. Let's have a quick look at it. How are we going to deal with such problems? Okay, the first problem we're looking at is a problem that comes from, I'm going to drag it here, a problem that comes from 2012 Euclid question number 9b. Okay, question number 9b part. So let's have a quick look at it. Also, I'm going to show you, as long as you're reading the problem, what kind of things you need to highlight. So I'm showing you. In the diagram, a quadrilateral ABCD has point M and N on AB and DC respectively, with AM over AB equals to NC over DC. Let's have a quick look at it. AM over AB is the entire thing, NC over DC. Okay, I don't know what is that for. Okay, let's park it there. Line segment AN and DM, they intersect at P point, while BN and CM, they intersect as Q point. Okay, proof. Okay, that's it. With no condition, let's go for the proof. Prove that the area of quadrilateral PMQN, what is the PMQN? Let's try to highlight it. PMQN, that's the, okay, that's the weird quadrilateral here. Okay, the area of this PMQN equals to the sum of the area ADP here, and also BQC here. All right. Okay. So basically the question gave me a kind of like quadrilateral to have some lines. There's a weird relation, a proportional relationship, which I don't know for now. I'm just going to park it there. And a question asked me to determine the blue one equals to the summary, equals the sum of the two red one. Well, the blue one and the two red ones, they're kind of like a pretty tilt shape, right? They're basically flying there, not touching with anyone. How can I possibly determine the area for those three shapes? I totally have no idea, right? So basically, this is a common strategy. As long as you see some weird shape, they're not a quadrilateral, they're not like a regular quadrilateral, they're not a very nice triangle, there's kind of like weird things flying there. Maybe the area cannot be determined directly. You can try to do some conversion and compensation. What does it mean? Means you have to really maybe add something or subtract something to make sure the entire shape is easier for you to do the calculation. Otherwise, if they're flying there, you totally have no idea what to do, right? All right, that is something you need to bear in mind. But in terms of how to use this real relationship, let's park it there. So how to do this? I'm going to show you a very easy peasy way to solve the problem without having writing a lot. So your point is want to show, right? WTS, want to show. You want to show the area of PMQN is the same as the sum, as triangle ADP plus triangle BQC. This is you want to show. But like I said, they're actually flying there. You kind of need to do some compensation to make sure there are something going to be more tangible. So what is the compensation? You always want to find out the overlapped part or something in between, make your life easier. So what I'm going to do is check it out. This two green part. Change the color to green. This is a green part. This is one green part triangle. This is another green part triangle. Okay. Because I really have no idea how those two flying parts there, right? The blue and the two red. So I'm trying to say, if I want to show this, then what about I add these two green parts on the two sides of the equation? If I can prove that, I can automatically prove the question asked me to do, right? So that being said means I just want to show PMQN plus triangle PDN, the big green part, plus triangle QNC, the small green part, equals to ADP BQC PDN QNC, right? I'm going to highlight it using here. These are the two green parts I just added here, right? Makes sense, right? Add two things on the two sides of the equation holds. But even though there are like two parts that are added on two sides, you think it's the same, but that's going to change your calculations significantly. Check it out. For now, the blue part adding the two green parts become what? It becomes, if I use the color here, this black triangle, right? Easy peasy thing, but it has been changed a lot. So I'm gonna say, now you just have to say, want to show these two parts become triangle MDC, the big triangle. And let's continue. The red part on the left, the red small triangle on the left, reaches what? ADP. If this guy plus the PDN, the big green triangle, so that part is going to become here, right? It also becomes a triangle. Okay, that's easy. I'm going to say here, this is going to be your triangle ADC. And what about these two parts? The red part on the right and also the small green part. So these together is going to become what? B and C, right? All right, so that's actually easy, right? So that's going to be what? Your triangle B and C. Now, previously, you're actually dealing with 3 flying stuffs, 2 flying triangles, 1 flying quadrilateral. But now you have already converted into 3 big triangles. They're basically lying on the ground. Then at least your life can be much more straightforward. So this is kind of like a conversion and compensation. So let's try to see how you're going to determine the M, D, C, A, D, C, and B and C. From here, I don't think I have too much tricks, right? I just have to basically try to maybe find out their height. So for my DMC, I'm going to find a height. So my height will be M. So for the ADC, I'm going to have ADN, excuse me, ADN, right? So ADN, I'm going to find a height. Maybe I call it A, right? From the BNC, I'm going to find a height. Maybe I'm going to say this is B, right? Because I really do not have too much information. I just want to put it there, right? And maybe I'm going to call DC. Let's try to give a value. Excuse me, please help to mute yourself. Okay, this is an open lecture. I can't mute you guys, so please help to mute yourself. Thanks for collaboration. Okay, so now let's have a quick look at it. Maybe I'm gonna call DC. I'll give a name X. Just try to make my life a little bit easier, right? And for DN is only part of X. I'm gonna say maybe TX. So of course this is gonna be 1 minus TX. Nothing special. It's only a quick calculation. Try to make my life a little bit easier. So let's have a quick look at it. What is the denotation for my triangle DMC? That's easy. DMC is actually 1 over 2. Your bottom is DC, which is X. Your height is your M, right? And what is about my area of triangle ADN? ADN, the bottom is DN, right? 1 over 2 DN. DN in our case is TX. And the height is actually A. Easy peasy, right? Last one, BNC. BNC, 1 over 2. The bottom is 1 minus TX. And the height, what about the height? The height is B. Very easy, right? So therefore, you just want to make some quick simplifications, right? You see, you have X, 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 all the X will be canceled, right? So not something too complicated. Do some quick manipulation. You will have to show M equals to TA plus 1 minus TB. You want to show, right? Because you don't really know how it is working or not, but you just want to show this. All the way come to here, very understandable. Okay, so here is, let's say I'm going to start, okay? Now my goal is try to find out how can I prove such a relationship. I think everything that I have done using the compensation ends from here. How can I find out the relationship for the red one? Before I do that, we have to have a quick observation. There are 2 things. First, there's a relationship given by the problem. I didn't get a chance to use them yet, right? Second, which is way more important, we're going to talk about our conditional react. In our lecture, we're going to talk about so many conditional react. Conditional react means as long as you see something, there will be something automatically pop up. You don't have to think every single time. But as long as you see the shape, as long as you see the condition, you will automatically have such a thing triggered. What is that? You see here, you actually have a trapezoid. Is it right? This is a trapezoid. Okay, here is a conditional react. As long as you have a trapezoid, okay, let's say A, B, N, E. You have a point. This is M, this is F, okay? I just want exactly the same denotation, okay? As long as you have a trapezoid. So normally speaking, the trapezoid is gonna give you A, B, maybe this is M, whatever, right? Okay, as long as you see a trapezoid, your conditional react is try to make a perpendicular line from the shorter side all the way to the longer side. Okay, as long as you see a trapezoid, you always want to make a perpendicular line from the shorter end to the longer end. Then automatically, let's say I'm going to give a name, maybe R here. You're going to find this triangle, the green triangle, is actually similar to the black triangle, right? This is something very understandable. AKA, as long as you have two triangles similar to each other, you're going to have what? MR over B, let's say I give a name, BD, will be equals to AM over AB. Is that right? MR over BD will be equals to AM over AB, right? This is something very important, okay? So this is a conditional react, like I said. You don't really have to think about too much. You might use it, you might not use it, but put them out right away. Okay, if that's the case, let's try to use the conditional react. We have, I'm gonna drag it here, see, all the way this guy. I'm gonna take a quick screenshot. One sec, I'll be able to use it in our next slide. Done. So we come to here. We just like to show you how to use the most straightforward way to do your writing. Don't spend too much time. Don't do the very weird writing. That's gonna cost you a lot of time. Because we have such a conditional react, then automatically, like I said, I'm gonna have what? I'm gonna have my AM over AB will be equals to MR over B, maybe BS. I'll give an example here, right? Maybe this is S. Okay, AM over AB equals to MR over BS. Okay, what is MR over BS? MR is exactly the difference, M minus A, right? This is your MR. Then what about your BS? BS is exactly the difference, B minus A, right? This is what you have. Then what about AM over AB? Do you think AM and AB looks a little bit familiar? Yes, AM over AB is exactly another condition given by the problem, right? AM over AB equals to NC over DC. So this guy equals to NC over DC. What is NC over DC? What is NC over DC? NC is here, DC is my entire thing. So NC over DC exactly equals to 1 minus T. Is that right? So therefore, you have M minus A equals to B minus A exactly equals to 1 minus T. You know what? You don't have to waste too much time. As long as you do some quick simplification, this guy, you just have M equals to TA plus 1 minus TB. That's it. That's exactly what the star equation wants you to show. It will say this meets the star expression. Therefore, QED. That's it. You see, you don't have to write a long essay to solve the problem. Just like a quick line, only a couple of lines, you are good to go. Okay, so this problem actually teaches us a very important conditional react. As long as you see this, a trapezoid, always want to make a perpendicular line from the shorter end all the way to the longer end. Then you will automatically have such a relationship. So trust me, this one is going to be very helpful when you have two circles externally tangent to each other. You're going to do exactly the same thing. No worries, we're going to save that for our next lecture when we're talking about the circles. So this is actually our conditional react number 1 we like to talk about in today's lecture. So today's lecture, we're going to talk about a lot of conditional react. And you're probably going to remember all those conditional react before you can basically solve all the problems. You see, using the compensation, you'll be able to solve something pretty weird by using something quite easy. Okay, that's our sample problem number 1. Okay, if all good, let's go to our sample problem number 2. Exactly the same strategy. I just want to show you how you can use all the conditional react we talk about in order to solve some relatively difficult problem. Question number 2. Question number 2 is actually a very difficult problem, to be honest, from the Euclid statistics perspective. But trust me, using the technology we introduced in our lecture, this is something so easy. So the second problem, you're looking at a problem that comes from 2013 Euclid, question number 9. Okay, this problem actually there was only a very little score acquired by the different students. So this question a little bit long, but let's have a quick look at it. For the first part, the question says you have a square xy, wxyz has the side length equals to 6. Okay, this is like actually joined. This is actually joined here, 6. Okay, completely inside a larger square, EFGH, which has the length basically goes to 10. Okay, 2 squares, they're basically one after another. The one is inside the other, and such that the squares does not touch each other, and WX is parallel to EF. So that being said means what? Means this line and this line, they're parallel to each other. Okay, no problem. Okay, with all of this, you need to prove that the sum of the area of the trapezoid EFXW. Let's have a quick look at it. EFXW. That's the red one, right? And the trapezoid GHZY. GHZY. Okay. The sum of these 2 trapezoids does not depend on the position of WXYZ inside EFGH. Okay, it means that as long as you are inside the small square is inside a big square, then you are good to go. Like the difference, like if the small one is actually inside a big one, regardless the position, the sum between these 2 red trapezoid will be a constant number, something like that, right? Well, I think this problem is fairly easy, fairly understandable, because if you want me to determine the sum of these 2 trapezoid, I'm just going to do some calculation, right? There's no way around. I just have to calculate and then tell you the number is actually independent with the position. So let's have a quick look at it. How are we going to determine? So we know the area method for trapezoid. Okay, so the area of trapezoid, let's say EFXW. So that one is going to be what? 1/2, the top plus the bottom times the height, right? 10 plus 6 times that part. I'm going to give it a name, maybe H1. Okay, H1. Then what about the trapezoid of the lower one? ZYGH, 1/2, 10 plus 6 times H2. You're going to multiply them together. You're going to add them together, right? That's going to be 1/2, 16, and then H1 plus H2. H2 is here. H1 plus H2, because you have a 1 square inside another square. So what is H1 plus H2? That's easy. H1 plus H2 exactly equals to 10 minus 6, right? The difference between these 2 square will be H1 plus H2. Regardless how you're going to move the smaller one inside, it's going to be always the same. So AKA, that one is going to be equals to 32. That's it. So easy, right? So think about it. If you can do, this is question A part of 9. It's so easy. If you can do this part, you will be able to get at least 3 to 4 marks, right? These are the easy peasy marks. These are the free given marks. Don't really abandon them. Try to use them. Okay, this is like so easy. However, the second part might not be that easy. So let's have a quick look at it. The second part is, I think it's kind of like similar as the first one, but this time you see the internal square has been tilted, has been rotated, right? So the second problem says a large square ABCD is actually drawn with a second smaller square PQRS completed inside such that there's no touch. The line segment AP, BQ, CR, DS are shown, dividing the region between the square into 4 non-overlapping convex quadrilateral, which makes sense, right? You basically divide it into 4 parts. Okay. If the side of PQRS is not parallel, okay, previously it was parallel, right? But now it's not parallel, okay, to the side of ABCD. Prove that. The sum of the area of the quadrilateral APSD, let me use the color, this guy, and BCQR, this guy. Okay, so these are the sum between the two red equals the sum of the area ABQP. Let me change the color. ABQP, this guy, and the area of the CDSR. CDSR. Okay. So the question says, if you have like a rotate, right, square in the middle, the question is going to ask you to prove that the 2 blue parts plus the 2 red parts will be the same. That is something looks like so strange, right? Because like the 2 red and 2 blue, they're totally weird shape. They're not something you can do the calculation. How can I do such a problem? Before we get started, I want to say this is our conditional react number 2. Conditional react number 2. As long as you're doing a problem like number 9, any solution you get from A must be applicable for your B. Any condition, any solution you get from the A part must be useful for the B part. Okay, there must be a correlationship between the A part and also the B part. But how can I use my A part? My A part is kind of like something parallel, a very regular, very straight, right? But like the second part is kind of like tilted. How can I basically use my first condition, the A's condition, A's conclusion, to apply them into the B part? That's actually $1 million question, right? Actually, try to do this. You're going to do some conversion compensation. So that being, of course, you won't be able to determine the 2 blue and 2 red right away, but you kind of like doing some conversion compensation. Plus, you try to use the condition you just get from the A part in order to make it happen. So the $1 million question is, how can I get from the A part? How can I use whatever I just got from the A part? But in order to use it, you need to have an A part, right? How can you construct an A part? You need to do some auxiliary lines. So, because for now, the PQRS is not parallel, right? Then I have to create a parallel line to make it work. How can I create this parallel line? This is what I'm going to do. I'm going to make a parallel line to here, to here, to here, to here. No, I'm actually by force, right? I create such a thing. As long as I'm done, I'm going to do a quick connection. Okay, I'm actually adding like 8 different auxiliary lines, but at least after this 8 auxiliary lines, I'm actually gonna kind of having something similar with my first part. Is that right? Trust me, the following part, there won't be anything too complicated. As long as you have such a shape, try to use some compensation, some kind of conversion, you will be able to solve the problem fairly quick. You know what? I'm gonna give you a graph, a more detailed graph after this kind of auxiliary line. Okay, let's have a quick look at it. Okay, now I'm gonna have such a thing. It looks like I create a square in the middle. So this square is actually outside my PQRS, my tilt square, right? There's a thing basically cover it. Okay, so as long as you have this, I think I'm going to talk about our number 3 conditional react. Number 3. As long as you have 2 squares, one is after another, one is inside the other, I will say something like this. I don't know if you guys can agree with me or not. I will say these 4 triangles, they are actually congruent to each other. Is it right? Do you agree with me? I think this is not a rocket science, right? These 4 triangles are actually congruent to each other. If you do not understand, I'm going to give you something very easy peasy explanation, just like a one-liner explanation, you're good to go. I have a square. I have like something like that, right? So let's say I want to prove these 2 triangles, they're congruent to each other. This guy equals to this guy, right? It's a square, so of course all the sides are the same. And also, you see, this is 90 degrees. This is 90 degrees. This guy plus this guy, oops. This guy, number 1, plus number 2 equals to 90 degrees, right? Angle 1 plus number 2 equals 90 degrees, of course. And also, number 2 plus number 3 also equals to 90 degrees, right? Of course, they're within the same. Number 2 plus number 3, they're within the same right triangle. So automatically, number 1 is equal to number 3. So check it out. Number 1 is equals to number 3. The 2 black sides are the same. Plus, they have a shared, I mean, this is not a share, but they have like the same 90 degrees. So the red triangle is actually congruent to this right triangle. Is that right? And you can do the same thing for all the other triangles. So AKA, these four triangles, they're actually congruent to each other. So I'm going to put it here. Okay, this is something. So if they're congruent to each other, means E equals to F equals to G equals to H, right? If I use the EFGH to present their area. Second, because we just mentioned, we want to, this is what I did. I did the entire thing, the purpose. I tried to use the condition I did in the last problem, right? So last conclusion is what? The 2 red part, their sum is actually constant. I think if the 2 red part, the sum is actually constant 32, I think the 2 blue parts is also the same, right? They're exactly the same thing. This is what we get from our last question number 8 part. The 2 red plus the 2 red, their sum is 32. The 2 blue, the red is also 32. So I spent so much time doing such a thing as I definitely want to use such a conclusion, right? If I do not use such a conclusion, why do I bother to do this, right? So that being said, what is my condition? So that being said, I'm going to try to do this. I'm going to use the color maybe blue. This is my first part. The blue plus the blue equals to 32, right? AKA, this is a constant. I'm gonna highlight it here. The blue plus the blue equals to what? The green plus the green, right? Blue plus blue equals to green plus green. This is what we got from the first problem. Of course, you're going to know that. I'm just going to highlight it, right? I'm just going to highlight it. Okay. So this problem, if you know this, solution is actually so easy. The blue plus blue equals to green plus green. So this is actually from our condition from question A part, blue plus blue equals to green plus green. AKA, I'm just going to put all the values there, right? A plus R plus C plus N, AR, CN, blue plus blue, equals to green plus green, B plus M plus D plus S. And they are both equals to 1/2 X plus Y, X minus Y. Let's say if I give a name, this is X, this is Y, right? The question doesn't really ask you the value. As long as you know they're the same, that's it. So now I'm gonna do another quick thing. Let's have a look at about this. The question asks you, what is the question asking for you? The question asks you, want to show is the area ABQP plus the area CDSR equals to area BCRQ plus the area APSD. This is what the question asks you. Those four things, adding them together is the same. Is in this graph, the blue one plus the blue one equals to green one equals to like the red one plus the red one. If we come to here, it actually means what? If I just plug in all those areas, that one is going to be what? A plus S plus E equals to C plus G plus M, B plus F plus R, D plus H plus M. This is your want to show, right? You just want to show this. Let's have a quick observation. This is what I have. Number one, 1 star, 2 star. 1 star is from our conditional react. They're the same. 2nd star is from our first conclusion. I just want to use the 1st star, the 2nd star in order to prove this maybe question mark. That's it. As long as I can do that, my work is done. Let's have a quick observation. What are the gap between the two? You have the A plus R plus C plus N, B plus D, B plus M plus D plus S. But now it has the E, G, F, H. Something like here, right? If you add here to here, you might be able to see something. Second, let's have a quick look at it at this part. Let me ask you something. For this black, very small black one, R, very small black one, N. Let me ask you something. If I wanted to ask you to determine the area, what is the area between the R plus N? What is the area between the R plus N? R plus N is actually, because R is actually QX, right? Times, I don't know, like the height, I'll say H1. 1/2 H1, right? Then what about the area for N? The N is going to be SZ, 1/2, maybe H2. Okay, I'm going to call this H2. Because we just talked about the 4 right triangles that are congruent to each other, aka QX is the same as ZS, is the same as WP, is the same as RY, right? So therefore, I can do some quick extraction. I'm going to extract out qx, which is h1 plus h2. h1 plus h2, is this something quite similar? h1 plus h2 is exactly equals to x minus y, right? X is the outer square side length, y is the inner side length. Okay, 1/2 qx times x minus y, that's r plus n. Okay, if r plus n is 1/2 qx times x minus y, this guy, I'm going to change a different color, maybe to yellow. So this guy, my s and my n, they are exactly the same thing, right? They're exactly the same thing. So that being said, my r plus m also equals 1/2 qx x minus y, because they're pretty much the same thing, right? If you just tilt, if you change your screen, right, like 90, you rotate your screen 90 degrees, so they're exactly the same thing. So that being said means what? That's a very interesting thing. R plus n equals to s plus m, right? This is s plus m, right? R plus n equals to s plus m. So check it out. Besides a, b, you have r plus n equals to m plus s. Okay, I'm just gonna call it maybe number 3 star. You know what? I'm gonna do this work simply using this 3 expression. I would be able to derive my question mark expression. Let's have a quick look at it. It's not something too complicated. So I have put it here, a plus r plus c plus n equals to b, maybe I'm gonna put it here, equals to b plus m plus d plus s, right? Okay, I'm gonna add a g, add a e here, because g, e, f, h are the same. So this is gonna be h plus f, okay? And because you are telling me that r plus n equals to m plus s. So what I'm gonna do is, for this guy, I'm gonna add m plus s. I'm gonna minus r plus n. This is gonna be 0, right? These two things are the same. I add one, I add a left, or I subtract the right. It's the same thing, right? I'm gonna do the same thing, but this is gonna be r plus n minus m plus s. I add the left, subtract the right. This is I add the right, subtract the left. Nothing has been changed, right? Trust me, if you make a rearrangement for this guy, this is going to be a plus s plus e plus c plus g plus m. If you rearrange this guy, this is going to be plus f plus r, d plus h plus n. This is this is exactly what the question asks you to prove. Exactly what the question asks you to prove. Okay, so this is actually QED. You can say because, therefore, QED. That's it. You see, you only need 1, 2, 3, 4, 5, 6, 7 lines, and you solve the problem. You see, this is again using the compensation. Okay, let's have a quick recap of what we have learned in this problem. Your conditional reactor number 1, as long as you see 2 parts, A part, B part, whatever you get from A part must be very helpful for your B part. You have to use it. This is something very important. Okay, always try to use the condition from the A part and try to solve the problem in the B part. If you do not have the A part directly, you're probably going to do some construction. Construct out your A part. Okay, first. Second is you want to actually see, as long as you have such a shape, a square has another square inside, your conditional react is you're going to have this 4 triangles. They are congruent to each other. You might use it, you might not use it. It's okay. You just basically park it there. These are the conditional react. And number 3 is this problem, even though it looks a little bit crazy, but this is only a compensation and conversion of different areas, right? You have 2 areas, you have like different colors, but try to use the compensation. You want to use whatever you have to prove whatever you do not have. This is something very, very important. You see, you're not really writing a lot of lines. You just write out this. This is totally, totally good enough. You know what? If you check the official solution from Euclid, I'm just going to give you official solution from Euclid. I just want to show you the volume. There's a huge volume. You know what? Just like I said, not to say you want to think about it. You just copy that within 2.5 hours. That's gonna be very challenging. Okay, this is actually another problem I'm going to show you here. So that's actually cut. I want to show you the official solution from the Euclid. That's our in one part. Okay, so I didn't really copy that, but trust me, if you go there, you're gonna find out there's a huge page. They put a lot of efforts doing the calculation. There's a lot of overhead, but using our solution, using my methodology, is a lot more straightforward. You don't really have to do too much work. Everything will speak for itself automatically. Okay, so try to understand, this is considered to be a very difficult problem for our 2D geometry, because generally speaking, 2D geometry won't go to question number 10. So question number 9 will be the maximum, will be the upper limit, okay? Because question number 10, they barely go for 2D geometry. So this is considered to be the most complicated problem for all the 2D geometries in Euclid. But you see, the solution process is very understandable. We're not doing something too crazy, not a lot of rocket science, right? So try to understand how to do this is actually something very important. All right? So I think 2 examples is good enough. I always give you the difficult problems. Already give you guys idea how to deal with the 2D geometries. As long as you're dealing the area, try to do some compensation. As long as you're dealing with some weird area, not like the very strict area, try to do some compensation. And the compensation is always sometimes using whatever you learn from the first problem and try to construct it in your second problem. This is our overall strategy I like to show you guys. So far, so good? If all good, let's go to our second category. Our second category is actually using the trigonometry. Sometimes the sine law, the cosine law, so on and so forth. So using the trigonometry, sometimes they can really help you to reduce the complexity of the calculation and help you really expedite your entire delivery. So let's give you one example. You understand where I come from. That is a problem that we have from 2018 Euclid, question number 8, B part. 2018 Euclid, question number 8, B part. So let's have a look at it. The question says, in the diagram, you have a rectangle PQRS. It's placed inside a rectangle ABCD in 2 different ways. First, you want to make sure Q at B, R at C. So basically, it's here. So the small rectangle is actually basically put on a corner, right, on one side of the big rectangle. And the second way is P on AB, Q on BC. You just tilt it. Still the same rectangle, right? But you want to tilt it. Okay? No problem. If AB is equal to 718. PQ is the same as RS, right? 250. With all those information, the question asks you to determine what's the length for BC. What's the length for BC? How to determine the length of BC? You know, normally speaking, you can directly give a value, maybe BC is X, right? And try to do some calculation. So this is actually what this official solution gives you. I'm just going to give you a quick idea how the official solution looks like. The official solution is very lengthy. Okay, basically, I'm going to show you something fairly quick. The official solution basically want to ask you for 3 different variables. You want to set one is, see here, one is A, one is B, and one is X. Okay, doing a lot of calculation. You have like 3 different variables, and then he asks a lot of like calculations, different kind of like equations together, try to basically figure them out. It's very lengthy, very complicated. I think there's a lot of calculation. I don't think that's a very good idea. Okay, but you can imagine, right? See, there's a lot of things doing the expression here and there. However, if you can solve the problem using my way, only a couple of lines, fairly understandable. I'm just going to leave it here. I'm going to show you what I will do for such a problem, aka with the help of using a trigonometry. So how can I use the help of trigonometry? Let's have a quick look at it. If you say trigonometry, I need like a theta, right? I need an angle. So because we're having such a thing, I say if this guy is a theta, this guy is a theta, this guy is a theta. Is it right? This is exactly the same thing as our previous conditional react. I'm going to go back. I'm going to go back a little bit. Here, still remember, I give you guys the proof. How come angle 1 equals to angle 3, right? Because they both at angle 2 equals to 90 degrees. Is that right? So we're actually using the conditional reactor one more time. Check it out from here. Because theta plus phi equals to 90 degrees. Theta plus phi equals 90 degrees. Theta plus phi 90 degrees. So therefore, the 3 theta are the same. The 2 phi are the same. Again, this is our conditional react, right? You really have to remember all of them. You cannot really think about every single problem from scratch. You have to basically have everything automatically. Okay, so let's have a quick look at it. How are we going to deal with that? I'm going to drag it here a little bit. Okay, as long as I have the theta, I just want to make my life easier by solving 2 easy peasy equations. First equation, let's have a look at it about this dc. dc equals what? dr plus rc, right? Of course. But what is dr? dr is actually rs. Rs is 250, right? You know this. It's rs times cosine theta, right? 250 cosine theta. What about RC? RC is actually this guy. This guy is actually this guy, right? BC. BC times sine theta. Is it right? BC times sine theta is going to be your RC. Is it right? This is not a rocket science, right? Because QR is the same as BC. Because they were superpositioning all here. So here, this is also going to be BC. DC equals to dr plus RC, and dr equals to 250 times cosine theta, and RC equals to BC times sine theta. And DC, what is DC? DC is the same as AB. 718. Easy peasy, huh? Second part. I have already do a math for DC. I'm going to do the same thing for BC. I only have 2 sizes, right? I only have the 2 positions for me to have the equations. Then what about BC? BC is going to equal to BQ. plus QC, right? What is BQ? BQ will be PQ times sine theta. PQ is the same as SR is 250, right? Plus QC. QC will be BC times cosine theta. This guy equals to BC, right? Okay, check it out. This is no rocket science, right? You have one equation, 250 cosine theta plus BC sine theta, 780. Second equation, 250 sine theta plus BC cosine theta equals to BC. From the second, of course, you won't be able to solve it. You have like too many variables, right? But from the second equation, you can do a quick calculation from 2. This is number 1, this is number 2, right? From number 2, you can find out BC equals to 250 sine theta 1 minus cosine theta, right? I call number 3. And then what are you going to do? Put number 3 into number 1, right? There are not too much things you can do. Plug number 3 into number 1. If I plug number 3 into number 1, what are you going to have? You're going to have 250 cosine theta plus BC, 250 sine theta 1 minus cosine theta, then times the sine theta, sine square theta, equals to 780. Okay, sine square theta equals to what? 1 minus cosine square theta. 1 minus cosine square theta and 1 minus cosine square, or 1 minus cosine square theta, they will be cancelled with the 1 minus cosine theta in the denominator, right? 250 cosine theta plus 250 1 plus cosine theta. 718. Is it right? This is easy, right? You can use a square minus b square equals to a plus b times a minus b, and you can cancel this 1 minus cosine theta. So therefore, cosine theta will be 117 over 125. Yeah, there are some calculation. As long as you know the cosine theta, plug in to 3, BC will be equals to 1375. QED. Check it out. My solution and the Euclid official solution. The complexity, you can tell them right away, right? Think about how much time you're going to spend in this problem if you're using the Euclid solution. And how much time you're going to spend in this problem if you use my solution. So these are the huge difference. So in our lecture, we actually focus, in our regular lecture, we spend a lot of time talking about how to use this shortcut to solve the problem, right? So this is actually a very good example. So using the trigonometry can significantly save your time. While using this, you're going to do a lot of like a perfect squares, a lot of things, because heavy calculation all over the places, you see? So I don't even bother to check their official solution. So this is actually a shortcut way how to solve our problems. So far, so good. All right, since we're running out of time, so we won't give you like too much examples for the second category. So using the trigonometry will be a very helpful way for you to solve the problem. In today's assignment, I'm going to give you another problem, a relatively difficult problem. You'll be able to see how to use the trigonometry to expedite the entire delivery process. Okay, that's our question, category number 2. Let's go to our category number 3 to wrap up today's lecture. Like I said, areas ratio is going to be the similarities ratio. You want to take a perfect square as long as you want to see, as long as you see similar triangles. Trust me, this one is not only used for Euclid, AMC, all those kind of math competitions across the world, they use this very often. This is something very important. So let's go for our sample problem for such a thing. This is a problem that we have is a problem from 2001, Euclid, question number 9. Like I said, most of the problems given by our lecture, it is the last 3 problems, 8, 9, 10, because they're challenging problem. I like to show you guys the thinking process for such a problem. Okay, so let's have a look at it, how this problem says. A triangle ABC is right angled at B. Highlight all those information. I'm going to use the color red. And has the side lengths which are integers. Side lengths which are integers. This is a very important condition. You know, side lengths does not have to be integers, right? 2.5, 6.9, they're all good. But why they're integers? So this is actually our conditional react number 4. As long as you see something, they do not have to be a integer. But the question give you as an integer. Most of the time, this problem might get involved with some number theory related discussions. If a value has to be integer, like triangles, number of sizes, right? Like the length of people, like the number of people, they have to be integer. It doesn't matter. But if there's something does not have to be integer, but the question give you this as integer, you need to have some kind of like conditional react. There might be some number theory related discussion. In our Euclid territory, number theory most of the time means factorization. In AMC, it might be different, but that's going to be like a total different story. But for the Euclid, factorization is the major part of our number theory. So these are all conditional react. You need to pick them up while you're reading the question. So let's continue. A second triangle PQR is located inside a triangle as shown, such that its sizes are parallel to the sizes of ABC, and with the distance 2. Basically, everyone is like offset by 2. Determine the side lengths of all possible triangle ABC such that the area of ABC is 9 times of that of PQR. The area of ABC is 9 times of that PQR. So the area of ABC is 9 times of triangle PQR. So we know these 2 triangles, they're similar to each other, right? I'm going to use the color red. My little red triangle in the middle and my big white triangle, they're similar because they're all like all the sizes are parallel to each other. As long as you see 2 similar triangles, their area has a ratio, then automatically the similarity ratio is going to be 3:1, right? Very understandable. For now, I think the question says the area of ABC is 9 times of the area of PQR. So let's have a quick discussion. Area triangle ABC. What is my area triangle ABC? My area triangle ABC, let me give a name. Maybe this is C, maybe this is A, this is B, right? So it will be 1/2 A times C, right? That's it. This is like from the big triangles calculations perspective. And how can I do that for the small triangle? For the small triangle, I want to get involved with the small triangle because you are telling me there's like 9 times difference, right? So what can I do is maybe something like this. Check it out. The big triangle's area can also be presented using something like here. I can use the blue trapezoid plus the green trapezoid plus the yellow trapezoid and also the little triangle in the middle, right? There are 2 ways to present it, right? There are 2 ways to present it. But let's have a look at it. Because I find out the area ratio between the big triangle and the smaller triangle is 1/3. So that means that if this is C, this is going to be C/3, right? If the outside is A, here's A/3. If the hypotenuse is B, this is going to B/3. This is something so easy, right? As long as you have this, I think there's nothing special. You can just try to do the calculation. The blue trapezoid is 1/2, 2 plus C plus C/3, excuse me, C plus C/3 times 2. The green triangle is 1/2, B plus B/3 times 2. The yellow one is 1/2, A plus A/3 times 2. Don't forget, there's a red one in the middle as well. 1/2, A times C divided by 9, right? You know what? You just have such a relationship. So this relationship, if you do a quick simplification, we're not asking something too complicated. A quick simplification, you're going to have AC equals to 3C, 3B, 3A. That's it. You just do some quick simplification, and that's it. And don't forget, you are having a right triangle, right? So ABC, there are some relationship for them. So B is going to equal to A squared plus C squared, right? Using the Pythagorean rule. You know what? You can basically plug in this. And then you can do some move the terms, doing some perfect square, try to get rid of the under root, which is not something so complicated. You're going to have all the way go to A times C minus 6C minus 6A plus 18 equals to 0. There's no trick. You should basically do some simplification, perfect square, you know, so on and so forth, hard calculation. You get this. As long as you get this, it's going to go to our conditional react number 5. As long as you see this, your first reaction is using the Siemens' favorite factorization trick. Siemens' favorite factorization trick. If you do not know what I'm talking about, do a Google search for that, SFFT. This is something we talk about from day one in our regular lectures, and AMC use it every single day. This is extremely important for AMC, and you could also use it because AMC and Euclid are a lot of similarities. This is the Siemens' favorite factorization trick. Try to do this, you automatically have A minus 6, C minus 6 equals to 18. Okay, this is the famous Siemens' favorite factorization trick. As long as you're done with that, what are you going to do? Because the question says integer, still remember integer? It means that AB, all the side lengths, they are integer. So AKA A minus 6, C minus 6, they're both integers. So what are you going to do? Very easy peasy, very mechanical strategy. Like a mechanical strategy, what you're going to do is you're just going to basically find out all the factors of 18 and then assign them to 6 and A minus 6 and 6 minus C minus 6, right? So A minus 6, C minus 6 might be 18 or 1, 9 or 2, 6 or 3, minus 3 minus 6, minus 2 minus 9, minus 1 minus 18. Or they can be alternative, right? Can be the other way around, 1, 18, right? Or 9, 2, just basically this guy come to here. Everyone take a swap, right? However, that one is going to go to our common strategy, our conditional react number 6. We talk about so many times. Apparently, A and C, they are the same thing, right? You don't really care what is A, you don't really care what is C. The question doesn't really ask you the value for like, what is A, what is C? So since A and C, they have the same position in this problem, you can do without the loss of generality, you can let A is greater than C. Is it right? Because you don't really care who is A, who is C. As long as you find out a solution pair, you're good to go. So this is also a very, very common conditional react when you're talking with all the number theory discussions. There's no need to list out all the scenarios. As long as you can make the, without a loss of generality, that A is greater than C, you are good to go. There's no need to cover all of them, right? So these part you can actually ignore. No need to swap them. No need to make a swap. You just take everyone A minus 6 is greater than C minus 6. You're good to go. 6, right? You're good to go. So try to solve this. This is going to be easy. A and C. A could be 24, C could be 7, 15, 8, 12, 9, 3, 0, 4 minus 3, 5 minus 12. Because you're talking about what? The side lengths of a triangle. These are all weird things, right? You can't have side lengths equal to 0. You can't have the side lengths equals to minus thing. As long as you have this, your B will be very easy to determine, right? Using what? Pythagorean triple. Still remember? You need to remember all of this. Every single thing we talk about in a lecture, they're useful. Voila, you have the solution. The question just asks you how many possible side lengths of ABC which can help you fit such a condition. That's all the condition solutions. See? Very understandable. Using two triangles, if they're similar to each other, the areas ratio is going to be the similarities ratio's perfect square. You can automatically have all those kind of things. All those kind of things. So easy for you to get. So that's basically what I want to say for our lecture number 1. Our lecture number 1 focuses on the triangles and quadrilaterals. Right? We're not talking about circles yet. We're going to talk about in our next lecture. So there are 3 major categories in this big chunk. Try to understand how to use the compensation and the conversion method to determine the area. Try to understand how to use the trigonometry to get all those areas, to get all those kind of calculations. This is very important. And also try to use the area ratio equals to similarities ratio's perfect square. So this is also going to help you to solve most of the AMs or most of the Euclid problems. So I think that's pretty much what I want to say for today's lecture. We actually have 100-hour free lectures upon request. You can take a screenshot for our lecture and ask your parents. This is like a WeChat. So ask your parents to do the WeChat thing, and our assistant is going to help you to send you all those free 100-hour lectures. All right, I think that's pretty much what I want to say for today's lecture. It's open lectures. We're kind of like running out of time for 8 minutes. Sorry about that, because we're waiting for the guys. We get started 5 minutes late, but generally speaking, it's a 2-hour lecture. And I hope you guys have some understanding how the Euclid math competition works. And that's going to be basically how to granularly understand all the concepts. And for each category, try to understand what is the solution strategy. All right, that's pretty much for today's lecture. Thank you so much for your patience, for your time, and I wish you guys good luck for your upcoming 2022 Euclid math competition. Bye, guys.
Excuse me.
So there's, yeah.
Hi, sorry, I just have a couple questions.
Yeah, maybe we can do that later. Okay, this is like open lecture. You can contact me afterwards. Okay, because this is actually like a recording. Okay. Can you do a screenshot, let your parents talk to me? I'll talk to you individually, not in this open lecture. All right?
Okay. Yep. Thank you.
Perfect. Thank you, guys. Bye.